Okay. Hello, everyone. Thank you so much for being here. So I'm going to talk about how to interpret and explain your black box model today. You can find my slides following this link. I will have a lot of links in this talk, so feel free to take a note of the slides. Yeah, so before I get started, a little bit about myself. My name is Sophia Yang. I am a data scientist and a developer advocate at Anaconda. My background is in psychology, statistics, and computer science. I know it's kind of everywhere. I am a big fan of the open source Python community and PyData community. I contributed to several open source projects and also contributed volunteer at various NumFOCUS, PyData, SciPy conferences. I also have a data science and machine learning book club. If you're interested in joining a book club, please join us. Yeah, we read one book a month, and then by the end of the month, we chat with the book authors. It's all async online, but the book author chat is online on the Zoom, real time. Oh yeah, this month we're reading Chip Yuan's book, Designing Machine Learning Systems, one of my favorite machine learning books. So check it out. So agenda today, we're going to talk about why do we care about explainable AI? What is explainable AI? How do we explain models and some tools you can use? Okay, let's get started with why. First of all, be able to explain a model facilitates decision-making internally and externally. Here's an example with LinkedIn. So LinkedIn has this model predicting customer churn or upsell. Like a lot of us, I don't know about you, but I, as a data scientist, I do a lot of churn models and customer models. So it's relevant, very relevant to my day-to-day job. So they have this churn and upsell model. And then when they give the result to their sales team's like, I don't understand this result. What am I supposed to do with this, right? Even if you're telling me, okay, this account is supposed to be churning or have a high likelihood to upsell, what can I do with it? I still need to investigate this account very deeply to figure out how am I going to talk to the customer and so on. So LinkedIn created this explainability tool called Crystal Candle to extract meaningful information from the model, the important features, and then created a narrative to the right here. You can see this account is very likely to sell because of the following reasons. So those narratives helps us, the sales team to be able to identify which product fits this customer needs really fast, and to be able to have a productive conversation with the customer. So explainable AI not only facilitates your decision-making for your internal stakeholders, it also facilitates decision-making for your customers. Here's an example of Booking.com. So Booking.com is a travel agency, I guess popular in Europe. It's like Airbnb, but also with hotel listings. So for each property listing, there is a what do you call it? Ratings for each property. And the property owners often ask, so why do I get a 3-star instead of 4-star? How can I improve my property to have a higher rating, right? So Booking.com use explainable AI methods to provide this highlighted features that your property are have this kind of rating because of the following features are highlighted. It also gives recommended additions to your property to the right here. You can see if you add those features, that might be helpful for improving your rating. So from those two concrete examples, I'm hoping you can get a sense of explainable AI is actually really useful in for internal customers and external customers. It also helps with regulations. A lot of times when we do our modeling, even if we don't have race, gender in our model can still be biased. Yes? Yes, that's a great question. So if you just use a simple decision tree, it's already explainable. You don't really need all those methods. So for LinkedIn, it's actually using SHAP and Lime. I think they're using a XGBoost plus some other algorithms. It's decision tree based, but also like not easy explainable. So yeah, so if you have a simple explainable model, you don't really need explainability techniques. But if you have like deep learning models or complex models or different models you combine together, then those techniques might be helpful for you. Great question. Yeah. So regulation. Yeah, we talked about regulations, and here I got some news articles here. You can see Apple credit cards assessment algorithm discriminate against women. So, so with our explainability techniques, it's possible to catch those kind of bias early on before model launching. Okay, so explaining our models is really, really hard. Debugging is probably even harder. Here is a model, image model detecting diseases based on your X-ray scan. During training, this model actually works perfectly, but in reality though, this model doesn't really work. And then what the researchers found through integrated gradient method is that this model is not actually detecting disease, but actually detecting the pin marks by the doctor. So that's how they were able to detect, right? This highlighted area are the attributed pixels predicting the likelihood of this patient having a disease. But the highlighted pixel is from the pin marks, not really from the disease. Okay, another big part is trust. You have to be able to trust your model to deploy it. How do you get your stakeholders to sign off your model? Can you just deploy a black box model without trusting it, right? So this is an example with Lime, where it categorized email to different categories, ethicism and Christian. You can see the words highlighted there are contributing to the predicted probability for the class, but the word choice is kind of irrelevant. So we can't really trust this model. And then finally, model monitoring. So in traditional model monitoring sense, we use a lot of like distribution related method, right? We track the distribution change, the model drift and all that, but it's not really getting to the internal work of our model. So one of the popular method is to track the feature attribution score. So how does this feature contribute to the model? How does this contribution change over time? So this is an example from Google AI. So you can see the trend of each features attribution is pretty stable. If you see a really big spike or down from one of the feature, it might be a problem. You might want to set some threshold to alert you if each feature, one of the features is changing dramatically in terms of their attribution. Okay, so I hope I have convinced you that explainable AI is kind of important. So what is explainable AI? At the core, it's the creation of explanations to create explainability for a model. It's the concept that a model's action can be described in terms that are comprehensible to whoever is consuming the predictions of the ML model. So when whoever you are, whatever, like if you are a customer, if you're in a sales marketing, you should be able to trust and understand your model. You don't have to be a data scientist to be able to use the results of the methods. Okay, so there are actually a lot of methods in the explainable AI research field. I tried to group them into different segments for us to better understand and also to better choose which method you want to use. So first of all, there is the model-centric methods and the data-centric methods. Model-centric methods uses focuses on the features and model internal architecture. Data-centric methods focus on external data or internal data, like if you change a data point, what would happen to this model? Or concept-based method, which is my favorite that I'm going to talk through later, TCAV, which is if you have this concept, for example, stripe, how is this concept of stripe important in predicting an image or classifying an image as zebra? Okay, so for model-centric methods, we also have post hoc and intrinsic methods. Intrinsic methods are inherently interpretable, like linear regression, adjusted regression, decision tree, generalized linear or additive models. So with those, we can basically just using their coefficients to explain. You don't really need fancy methods. And then we have post hoc methods, which also have local, cohort, and global. So for local methods, we're looking at why is this specific instance get predicted to a value. With cohort or global, we're looking at all the training data as a whole. How is this feature influence the whole training data? Global and cohort are pretty much the same. Cohort is just a subset of the global. And then I know it's a lot of information. For local methods, we can also break it down into model-specific methods. For example, integrated gradient only works for models that are differentiable, but model-agnostic methods works for any kind of models. You don't need to assume any model architecture or anything. It just works. But then you might think, okay, so I just want to use that, right? Whatever model I have, I can use model agnostic methods, but that usually comes with a cost. It will be more cost heavy if you use those kind of methods. And then the same thing for cohort and global methods, we can also break it down to model specific, model agnostic, and hybrid methods. Hybrid methods are just the aggregated local methods that we mentioned to the left. So yeah, so this is the landscape. I didn't include all the methods, but I think a lot of methods can be fit into one of those buckets. Yes.
So your prior foil, you talked about basically creating narratives for understanding for
Yes.
stakeholders.
Yes.
I see no narrative creation on that slide.
I'm sorry. Great point. Yes. Yeah, I think there are stages. You have to understand some of the things, methods first, and when we fully understand it, we can interpret it better for our stakeholders. I don't know how to make it more better understandable though. Any suggestions? Yes. Thank you. Yes, I should have ChatGPT to rewrite this. Thank you. Yes. Yeah, I think that's a great question. I think this is basically telling you what are you interested in. If you're interested in data-centric methods or model-centric methods, because a lot of those methods work for continuous data. It's like kind of different dimensions of like the one you're specifically talking about, continuous variables. Yeah, I don't know. I think each of those has its specific use case. For example, if you want to look at specific pixels, you use integrated gradient. If you want to look at a segment of pixels, you use XRAI. So it's like the nuance is very specific, those methods. So it's kind of hard. This is actually the standard way in research field to categorize explainable AI methods. But yeah, if you have suggestions, I'm all ears. I really like the flowchart idea. It's just like, yeah.
The foil is fine. I guess what is the ping pong you don't mind.
Yes, yes.
Part of what you're talking about with like the two-way t-test, that's the very earliest form of model explainability. Right? Very earliest form. And a paper was written. Again, my point is on the US still all flowchart. Well, there are plenty of people who think that hard about the two-way t-test, and they should, because it's not their normal way of thinking. And to you, it's natural, but it's not novel to other people. It's not. All of these models are really quite novel. Explaining how they work is really quite hard. So that's, to me, explainable AI is amazingly difficult. And I applaud you for attempting to even explain it.
Thank you. Yes, please give me suggestions. Yes. Okay. I love the conversation. Thank you so much. And thank you. Okay. So, okay, now you might wonder, how do I actually do this, right? I'm going to go through 4 examples, just intuition, although there will be some math. Hopefully you don't mind. So I'm gonna take a look at the tabular data example with SHAP, image data example with integrated gradient, text data example with LIME, and a very interesting and fun example, which is my favorite, TCAV method. And of course, SHAP, integrated gradient, LIME works for all types of data. It's not just the examples that I'm showing here, but I just want to show a one example to be simple. Okay, so how many of you know SHAP, Shapley values? Yay! Okay, quite a few people. Cool. So Shapley values came from game theory, basically calculates what's each player's contribution to a collaborative game. So players can join forces, form teams, but each player's contribution to this formed team can be different. For example, if player 2 and player 3 form a team, player 1's contribution to that team could be like 1 point, but then player 2, player 3, player 4 forms a team, player 1's contribution could be 2 points. The contribution could be different. So the gist of Shapley values in this case is just simply calculate the weighted average of each player's contribution to all possible coalition it can contribute to. So that's Shapley values. SHAP is the implementation of Shapley value. So in the machine learning and AI model sense, here is how the output will look like actually. Imagine we have a base rate, which is the expected value of your output, and you have a black box model, and now you have a data point, an individual of someone who is 65 years old, who is a female, and then this person got an output of 0.4, right? And then you might wonder, why is there a 0.3 difference? So can we use different attributions to explain this difference? So that is what Shapley value is. You can see the Shapley value here to the right for each feature. So BMI is 0.1, BP is 0.1, sex is negative 0.3, and age is 0.3. And if you add them together, it adds up to 0.3, which contributed to the 0.3 difference. So yeah, so you can see it's quite easy to explain. That's why SHAP is quite popular as a method. There are many, many ways to calculate Shapley values. Here's one way. Hopefully I won't confuse you. So for example, if we have 4 features predicting housing price, we have the house style, number of bedrooms, the number of bathrooms, house age, predicting house price, and we have this instance, x1, x2, x3, x4, predicting the house price of 330K. We want to understand why this instance get predicted 380K, 390K, and what's the attribution, Shapley value of, for example, number of bathrooms. So the way the algorithms work is we random sample one sample from our data, and we, which is Z1, Z2, Z3, Z4, which is irrelevant from our instance right now. And we permutate the feature so that you can see right now the X parenthesis 1 is actually, was actually X2. And we create those 2 instances, X plus 3 and X minus 3. You can see the only difference is the X plus 3 use the original value for the feature number of bathrooms. And that, the X minus 3 instance use the sampled feature, which is not meaningful for this instance. And we calculate the difference of the predicted value of those 2 instances. And we do this many, many times. This will give us the Shapley value for the number of bathrooms, which is the 3rd feature. I know. This is just one of the algorithms. Hopefully not too confusing. There are also other algorithms like kernel SHAP, tree SHAP, deep SHAP. Tree SHAP is for tree-based models. Deep SHAP is for deep learning-based models. I linked the SHAP documentation here. You can take a look at different methods and implementations of the Shapley values. Okay. So, any questions? Yes. Okay, like right now? Okay, yes. Okay, yes, I will give you the link. Okay, integrated gradient. So here's an example where we have an image that's predicted the cockatoo bird, and we want to figure out which pixel of this image tells us this image can be classified as cockatoo. And you can see the highlighted pixels are the contributing pixels. So yeah, so that's basically how it works. You can see it could be important in some use cases, like what we talked about, the image classification for diseases. So I know some math again. As you can tell from the name, it's a gradient-based method. However, if you use pure gradient, it doesn't really work because when your model figure out the classification of this image, any change in your gradient won't actually change your output anymore. It's called gradient saturation. So to solve that problem, what integrate gradient does is it creates a series of images along the straight line in image space from the baseline to the input image. So the alpha 0 is the baseline image. When alpha equals 1, that's actually the input original image you're interested in. So one issue with this method is that you might think, okay, why do we choose the black image as the base image, right? You could choose white image, you could choose a noisy image. Yes?
This is the alpha.
It's a different alpha. It's like how much, so it's a combination of your base image and your original image. If your alpha equals 0, means that there's no original image in this image. It's just like alpha, yeah, alpha times the input image plus or minus alpha times the original image, that kind of thing. Baseline image. Right. Right. What is? Yes, thank you so much. Right. So the baseline images matters. A lot of researchers found if you use different baseline images, the result will be different. So that's a big drawback of this method. And so that's the gist of this method. And the actual calculations actually approximated by Riemann sums. Here's calculations I'm not going to go through, but you can take a look later if you're interested. I included 2 links of 2 tutorials, use 2 different libraries. If you're interested, please take a look. And the third one, Lime, is also another very popular method. Anyone knows Lime? Okay, cool. Lime is local interpretable model agnostic explanations. It's basically using your to explain the model behavior in a local area. To use the explainable model is to approximate the model behavior for the complex model. So here's how it works. So you sample the points around the original inputs with slight perturbations. So the original point you're interested in is this red big plus sign, and all the other data points are your sampled data points. And then you fit an explainable linear model because the linear model is explainable. So we want to fit a linear model here on the samples weighted by their distance to the given input instance. That's why I can see some dots are bigger when it's closer to our original input points. And then you basically use this linear approximation to explain the local behavior of a complex model. So it's a very simple idea. You look at only the local area and use the explainable model to look at the local area. So in the sense of text analysis with text data, the perturbated examples are basically you create new text by randomly replacing words with spaces, and then you can fit a linear or explainable model fitting and explain the text the same way we explain our tabular data. But then you also need to remember we weighted the samples by their distance. So here you have to calculate a distance measure between the tabulated examples and your input examples. Cosine distance is often a method that people use. Okay, so that's Lime. And then here is the result of Lime that you have seen before. It highlighted the words that contributing to the prediction of the classification. Okay, I also linked a Lime tutorial here. Yes. Yes, so all those 3 methods so far work for tabular, work for image, work for text. So, but it's the integrated gradient is not model agnostic because it only works with models that differentiable because you're calculating the gradient. So all those CNN models works because they are differentiable at certain layers, I think. For SHAP, it depends on the algorithm. For example, kernel SHAP is model agnostic. It doesn't matter which model it is, but tree SHAP only works for tree-based models. It's more computationally efficient if you use it for tree-based models. Also, deep SHAP is designed for deep learning models. Yeah. So I hope that helps. Okay, the final method that I am super interested and excited to introduce you about. Who knows TCAV? Okay, nobody. Okay, yay. It's gonna be fun, yes. So this model is specifically for image, I think mostly. When we talk about integrated gradient, it's mostly talking about you're looking at attributing pixels, which pixels are important. But when you look at the pixels in the image, you kind of interpret those pixels from your own eye. Are those pixels related to the neck of the bird or the head of the bird? You're kind of guessing, right? You don't have evidence that those pixels are what concept you're thinking about. With TCAV, it's specifically designed for looking at concepts. So is the concept stripe important in predicting this image as zebra, as an example? So I find this very fascinating because it just makes sense to me. There are 5 steps to calculate TCAV. Sorry, it's a lot of algorithms and thinking. First of all, you have to define the concept of interest. For example, here, we need to define a data set of stripes, right? So this is actually the biggest challenge of this method, because finding a database of the concept you're interested in can be really difficult. There is a database out there. I remember the name, but I now forget. Okay, there is a database that this paper is actually using. Luckily, it has all the concept of stripes. It also has other concepts like zigzag, dots. Yes. 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 Yes, exactly. So you have your model separately. This is a separate data set. This is a concept data set that's irrelevant. Yes. Yes. So it's like completely separate. It's external. You have to find this data yourself. Yeah. So you define a concept of interest, which is stripe. And then the second step, I know this is step D, but it's actually the second step, I think, is to calculate concept activation vectors, which is the VCL here. How does it work? So we have this stripe database right here, the first row. The second row is random data, right? You feed both of them into your image model. If you look at layer L, you get the activations from that layer L. So you get the activations for both your stripe concept and your random image. And you fit a hyperplane or a linear classifier to distinguish between those two activations. And your activation vector is defined as this vector perpendicular to the hyperplane, or the classification boundary. So that's the activation vector. And then the third step is to calculate the directional derivatives, which means that any change in this vector, how much does it affect the model output, which also tells us the conceptual sensitivity. How sensitive is this model to the concept of stripe? And then we calculate TCAV, which means we do this for all our images. And then we look at among those are among the images that are classified as stripe, how many of those have a positive derivative scores? So which means how many of them are sensitive to stripe? And then finally, we statistically test the TCAV score. So we do this many times, one with our stripe, and with many different types of random images, we get a distribution. And the other case, we replace the stripe images with all the random images. So it's random versus random. And then you get another distribution as your baseline. And then you calculate whether those two distributions are statistically significant. So that's, you can do a t-test. So you can see whether the stripe is actually meaningful statistically. Again, I included 2 tutorials here. You can take a look with code. You can go through the code to see exactly how it works for your model. Okay, any questions? Yes.
Explain it like I'm 5 years old. Why? Can you go into detail on that seems like we're if you explainability.
Yes. Hmm.
I'm just now reading it, and a friend of mine, it keeps on saying that, so it just seems very, I like that as far as explainable AI, how can you bring it down to a level of 5 guys? And it sounds like that expression started about 2010, and the concept, I'm just trying to understand how it's distinguished with line.
Which one was line? TCAV?
Explain it like I'm 5.
Uh-huh.
That's what I'm hearing from a friend, and then also I'm reading about it, and I didn't know if you could distinguish that as a method or on it. And I'm finding my documentation on it.
Uh-huh. Online?
Yes,
okay.
it's ELI. Explain it like I'm 5.
Okay, so for line specifically, you have this complex model. You want to explain one data point. So you don't care about this model. You only care about this specific area around this data point. So you use a simpler model to explain the area of this one data point. Is that better?
Yes.
Okay.
Yes.
Yes. Yes. Yes, that's why you use cosine distance to calculate the space, the distances. Yeah, it's just an example. In reality, you're actually doing it in the vector space. You're not actually doing it in the words. Yes. Yes, yes, exactly. So you actually don't need to understand all the algorithms I'm talking about today. You actually only need to go through the notebooks if you want to use them and see, oh, here's the result. It gives me which the Shapley values for each thing. You don't really need to understand it. But if you want to, that's interesting. Yes. Right. Well, that's why it's a local method. You're only looking at this maybe one sentence at a time. Right. Right. A lot of people don't like line. Yeah. 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 I'm going to talk about how to choose. Not going to say which one I don't like, but there's some some competition in the areas. People have a lot of opinions. Yeah. Right. So it really depends on what you what you need, right? Like I said, if you want to look at specific pixels, there are different saliency methods. If you want to look at concept, there is TCAV. So different methods focus on really, really different things. So it it's helpful to understand each method, but at the end of the day, you just want to use it. And also, like, there are a lot of opinions in this field. A lot of people have strong opinions about line, for example, especially for image data. People say don't use line for image, but like the line researchers will tell you they're the best method, and they have novice things to make sure things are doing okay for images. So yeah, so that's that. If you, okay, I don't know why it's not showing. Oh no. Okay, I will give you the slides afterwards, but there is a book. this book, Explainable AI for Practitioners, actually listed all the pros and cons for each of the method. So it's a really, really good read. If you want to choose whichever method you like, you might want to read up to the pros and cons and make sure you have kind of a rough understanding of the method you're interested in. Okay, and oh, here we go. And Captum is a library, has a algorithm comparison matrix that you can take a look. Okay, finally, tools. Yeah, like I said, it's good if you understand the algorithms. It's okay if you don't. You can just use it. There are model-specific tools like SHAP, Line, TCAV, designed specifically for that one type of method. But then each type of method has their sub-methods. So you can read up on docs. Saliency library is great. It has 7 saliency methods. Integrated gradient is one of the saliency methods, and I like to just use them all and see different output from different methods. It's actually quite fun. Alibi explain interpretML actually combines a lot of different methods together, so you can use that as well. Captum is for PyTorch models. If you use PyTorch models specifically, just use Captum. And finally, there are a lot of vendors that give you explainability features. If you use AWS or GCP, just use whatever vendors will provide you. So yeah, if you want to learn more, those 2 books are really, really good. I recommend it. And our book club actually interviewed the book authors from Explainable AI for Practitioners book. They're really nice and knowledgeable. Yeah, take a look if you're interested. And here are my references. Thank you so much.
You don't? Yeah, don't invite me.
Well, thank you to both our speakers, Sophia and Amir. I don't know if this is, oh, okay. Thank you.